Excellent. So this is what I'm going to talk about today. A demo that we built a while ago. I think it was around May, something like that. And yeah, but first things first, my name is Martin Schufus. You don't need to remember the last name. You will find me under the name Useful Thing, Mr. Nell there, all over the internet. And I'm a software engineer from Hamburg in Germany. I think of myself as a teacher, tinkerer, maker, father. What I enjoy most is basically helping people advancing their skills. And I've been also very active in the Three.js community, for example, over the past years and helping people there. I've been in professional JavaScript development for about 20 years now. And since 2015, I work for a company called Labs. Labs is specialized in web-based applications all around maps and geodata. Was founded in 2007 and where we were among the first users of the Google Maps API when it was released. So our mission basically is to create the most beautiful and most useful maps for our customers and their data. And yeah, we always try to explore what limits browsers have today and maybe tomorrow, and see how we can push beyond them. So yeah, we love maps, data, and data visualizations. And just briefly, a very quick look into the history. This was made, I think, 8 years ago, when there was still all those problems going on with syncing Google Maps with overlays. And so when you move the map, you see the data on top, just moving behind it. It took several months to build. We needed to have like interactive heat maps for a car sharing company, I think, to explore usage patterns. And that was built with Three.js. 8 years before the real thing came out a year ago, we already had a Three.js overlay view for Google Maps. It's a heat map. It's not very spectacular. And just go to the next slide. That's the thing. We spent months building this. And today, thanks to companies like CARTO or Unfolded, deck.gl, and Kepler.gl, all of them, this is basically a turnkey solution. I just drop my data in there, and I have all these features readily available already. So it means the work that's already been done in providing all these features with deck.gl allows us to push even further and provide stuff on top of what's possible now. And especially the beautiful examples that deck.gl already has inspire us and our customers to come up with new ideas how we can visualize their data. Which brings us to this one particular customer. Hi, Alex. Where we built the global air traffic visualization for the Google I/O this year. And so this is what it looks like. We have like a website. We have a huge amount of flights, and you can explore the individual airports, and you see the flights moving. You can see that all in a context with a local time, basically, thanks to this overlay that's moving across the map. The colors are a bit weird. Usually you would see something here. Anyway. So the feedback we got most about this is, okay, yeah, that looks great, but what is so special about it? And this is what I'm going to talk about. So the briefing we got was basically, so we have this Google I/O thing coming up, and can you sort of like do anything that looks cool? And everybody dreams of these sort of briefings where you have like the full, you can do anything you like. But yeah, it's kind of difficult to do because key challenges around the data you use, the design, the performance, interaction has all constraints that we need to find for ourselves first. So let's start with the data. What data do we want to show? It's difficult to find a data set that is global, that you can freely use. It is so you don't run into legal problems, hasn't fallen from a truck or something like that. Yeah, we wanted to be able, because we wanted to show performance, and the best way to do that is to have animations running. And so we wanted these animations not to be like a beauty aspect, but really meaningful. So we need data of moving stuff. And yeah, and we wanted a data set that's global and not like what we often see is like the data sets from New York taxis or something like that moving around. And we wanted a global data set that's nicely distributed. It leaves us basically with two options, which is marine traffic and air traffic. Marine traffic is, I think, legally a bit complicated, but air traffic was a data set that we were able to obtain. Then for the design, with such a wide briefing, we need to see what do we want to achieve. We want the look to be really clean and simple. It has to be immediately understandable what it tells you. So there shouldn't be any distractions in the map or in the base maps or whatever. Then the next thing is the performance. It's all about that. We want to achieve no frame drops in animations, and that should work across a really wide range of devices, because we don't know with what device the users open the page. So we will choose how much data we actually show based on performance constraints and based on design aspects, as I will show later. And then, yeah, of course, we want to have some interaction, because if there wasn't interaction, we could just make a video. So we need to think of something that is useful, that is, provides information and doesn't require any additional explanations. So let me quickly talk about some of the highlights, for me at least, as some data nerd. So we got this data set with about 300,000 individual flights, was over 3 days, and I think it's really all the flights. That came in as 40 megabytes of CSV data, and we also had information about 3,000 of the larger airports in the world. Then for every flight, there's some ID we don't need, but we need the original destination airports, we need the departure time, and we need the flight duration. For some probably historic reason, all the times in air traffic are always local time, which is really weird to convert, because you never know if it's winter time there or summertime or which time zone. So it was a problem on itself. So the steps to prepare the data for use in deck.gl was, first of all, cleanup. There were some flights that just didn't make sense, where the planes would have had to fly like 1,500 miles an hour or something like that, so we just threw them away. Then we had some flights involving really small airports, and we just dropped them. We wanted to see a nice global distribution. So some smaller airports are in our set, but yeah, otherwise they were dropped. Then we had some flights that go over the poles, and if it exceeds 80 degrees in latitude, on the Mercator map, it starts to look really weird. We just didn't want to explain that, so we dropped those slides. Sorry. Then finally, we need to convert all the times to UTC, and then we selected a slice. It was like 24 hours based on the departure time. So we ended up with around, I think it was 20 to 80,000 flights that we had in our list, and 3,000 airports. So it was quite manageable in size of the data set. Now, in order to render them with deck.gl, we would have had, I think, two options. One was extend the arc layer or the great circle layer to allow us to animate them according to timestamps. And the other was to use the trips layer. But trips layers don't interpolate great circle. They just draw a straight line from one point to the next. So we had to create these great circle arcs manually. This all happens in a worker. So the great circles are interpolated. We have the intermediate time steps for everything. I think we ended up with 15 or so subdivisions for every flight. And in order to achieve a seamless loop that you can watch for hours without jumping or something, we duplicated all flights that crossed the 24 hours line and copied them to the previous day, basically, then chopped off the rest, and there we are. And finally, there's a problem with wrap longitude and the trips layer. So we had to split the geometries at the anti-meridian, so we don't run into any of those. Now, the trips layer is extremely inefficient by design. So how the trips layer works is it generates all the geometry for the whole arc, and this could be hundreds of triangles already. And then in the rasterizer, so in the fragment shader, it will discard most of it. So it will only actually render the few pixels that are actually where the current time matches the timestamp in the attributes. So if you have a really large number of trips in the trips layer, you end up with like 80% of the triangles that get sent to the vertex shader are just useless, basically. So what we ended up with is a time slicing solution where we split the trips by departure time into buckets of an hour each. So we could, at any time when rendering, we could check if there are any flights en route for any of those 24 buckets. It also happens based on the flight duration. So flights that take like 12 hours don't get sorted into the buckets; they get their buckets on their own. And that way, we could improve this efficiency of the trips layer by quite a huge amount. Then deck.gl has, with Google Maps, has an interleaved rendering mode and an overlaid, I think, on top rendering mode, where in the overlaid mode it has its own canvas, its own WebGL context, and renders independently of the base map. And the interleaved mode is where it uses the WebGL overlay view to integrate into the rendering flow of Google Maps. But the problem when using the interleaved mode is that when I'm running animations at 60 frames per second, I also have to redraw the base map 60 times a second, which can be quite intensive for the performance. especially if you're going down into a city context where there are buildings or stuff like that. But unless you're going into this city context, you also don't have any benefits from this interleaved rendering. So we chose the standalone mode, so where we render on top, so we could use all of the available resources for our animations and not for rendering Google Maps. And then finally, we also switched from the vector-based maps back to a tiled map. And this is something very beautiful about Google Maps, that you can use the same styles and just switch around between vector-based rendering and tile-based rendering. So it looks the same, but it uses a completely different infrastructure. And the tile-based maps are the most performant thing you can get there. Okay, and finally, a risky click of the day. This is one of the tools. So we've gone through a lot of iterations with those. And we built tools just to explore the design. And so what I can do here is, for instance, change the animation speed. And so this allows us to find just the right speed. We can, for the trips, we can just like take some more flights into this. But we noticed during our exploration, it looks too chaotic. I mean, obviously, it also starts dropping frames a lot. But also on the other side, this looks too sparse. So we have some filtering by flight duration here. And we can also adjust the trail length that we show and all of those parameters. So we built those tools just to explore how the design will look. And we have countless other of those examples where, for instance, now the colors are just randomly assigned to look beautiful. But we also had versions where we like by plane category, the colors, or by flight duration or whatever. But we ended up with the random look, I think is a really nice result. So back to the presentation. Oh, no. Yeah, this is what I want to end with. Making it look easy is the hardest thing in the world to do. Thank you. Any questions? Then who's next? Yeah.
You could mention about the 60 frames per second performance. I was saying that you briefly mentioned that you wanted to work at 60 frames per second. Yeah. But the thing is that not every customer has a powerful machine and so on. Have you evaluated any kind of smart hacks or approaches to determine the capabilities of the machine and probably limit the kind of the complexity of the computations required and so on?
No, so we actually thought about that to make that adaptive. That we just we had this slider to reduce the amount of flights, so we could have reduced the amount of flights if we notice the frame rate gets too low, but we didn't get to implement that. We just chose our initial parameters in a way that works on all of the devices we had available for testing. Always, smartphones are incredibly capable when it comes to GPU stuff. I'm always amazed by that. So you would think that those are the bottleneck, but it's probably more like a PC somewhere. Yeah, if there are no more questions, then.